they add in what they call cold start data. Looks like this. First, they collect some supervised fine-tuning data. Then they do the same kind of reasoning optimization that they did in R1-Zero. Then they take that model and they generate another synthetic data set of supervised fine-tuning data with rejection sampling. They then go back to reinforcement learning. So let's kind of dive into each one of those buckets. All right. Well, welcome everybody to Archive Dives with Oxen.AI, where each week we dive into interesting research papers in AI and ML and try to show you how you can apply it to your own work. And this week is no different. There's the big launch of DeepSeek-R1 from this lab in China, and there's just a few authors on this paper, so it was hard to mention just one. They kind of had research at DeepSeek as the main email, but just wanted to call out, look at these hundreds of people that made this work happen. And what's really cool is they open sourced the weights of the model, and it's reaching the performance of OpenAI O1. So lots of people are touting that we have these O1 abilities at home now. I realized that if you're new here, I actually rarely introduce myself or what my background is on these calls, so thought I might start with that. I'm the founder of Oxen.AI, and my background's deep in the deep learning space. I've been working on deep learning and machine learning for over a decade and was a part of one of the first deep learning as a service startups back in the 2010s, where we were productionalizing ALEXNet and some of these early small language models back when we had to write our own neural net libraries in C++ before the TensorFlows or PyTorches of the world. So I've done a lot of building models from scratch, taking them from research to production, and worked a bit on IBM Watson when they were pouring billions of dollars into that. So seen a lot of iterations of these AI models and a lot of the hype cycles of AI. So basically here to help break them down for you and share the knowledge. And I just love reading these research papers and sharing them with the community. So with that said, let's dive into DeepSeek. And I loved this little graphic that Matthias made of DeepSeek slapping OpenAI as Batman. But in January 20...
I found it on Twitter. So
Oh, you found it? I thought
yeah,
you made this.
I found it and make it.
That's awesome.
So it's still great.
And even if you go to their website, like front and center on the homepage is DeepSeek-R1 is now live, open source, and rivaling OpenAI's model O1. So that's not just Twitter saying that, but they have it on their homepage. And so in the spirit of archive dives, we're going to dive into the nitty-gritty details of the model. And I even put together, as I was doing this research, a little no hype reading list with all of the links to all of the archive papers that we've either gone over in these dives or I thought would be helpful as context for this dive. But I love to get started with just why is this a big deal? Why are people so excited? And there's a few reasons. The first one is just the pure dollar value of compute that they use to train the base model DeepSeek-v3 is $5 million instead of these hundreds of millions of dollars that have been reported for other closed source models or even the Llama series of models. So it really feels like they're flattening the closed AI monopolies. And even some of these models you can run locally at home. Well, depending on how many GPUs you have, probably not the full R1 or V3, but they've distilled a bunch of models to enable small models that you can run at home. And they give you full access to the reasoning traces for these models, which is pretty helpful for a lot of reasons. What I think is one of the more interesting takeaways from this, and I've seen this a few different places, like Gwern talked about this on one of his blogs, but much of the point of a model like O1 or R1 in this case is not necessarily to deploy it, but to generate training data for the next iteration of the model. So every problem that this reasoning model can solve is now a training data point for the next reasoning model. And what this means for the rest of us that might not have as much compute as OpenAI or some of these other labs is that R1 looks like it'll be amazing for distilling small models for your specific use cases. And at the end of the paper has some concrete numbers about this and takeaways there that we'll dive into. And I honestly think there's an interesting analogy between like the start of personal computing. It kind of feels like these big labs are now like the big mainframes that you have to pay for shared access on, and you can do little to customize them. But with DeepSeek and some of these Meta Llama models, it feels more like the homebrew computer club where you can download these things, customize them, tinker with them, run them locally, and really solve like specific problems that you might have without paying a big old cloud bill. So I think that's one of the interesting takeaways, and honestly, one of the things that we're helping enable at Oxen.AI is the ability to generate the synthetic training data, version it, put it into your models, and then put these smaller models into production. So if that's interesting to you, feel free to check out just Oxen.AI in general. We do a lot of work there. So before we go fully into the paper, I think it's good to define what is a reasoning model. And it's pretty simple. It's just like requiring the model to think before it speaks. So with R1 specifically, it kind of has this format where it has these think tokens. It generates some thoughts, it ends the thoughts, and then it puts out the answer. And I even have one of the smaller models running locally with OLlama right here, DeepSeek-R1 14B. So this actually isn't the largest of the suite of models, but is one that I can run on my laptop right here. And I was playing around with prompts just like use long division to find the answer to, and I just type in like a random number and then divide it by 13. And you can see it starts by thinking and it's walking through its steps, and then it starts to set up some long division, looking at the first digit, looking at the second digit, moving on. And this was like a crazy number that I just typed in, and I'd love to see if this actually gets it in real time. There we go. We're walking through each step. Final answer. I definitely can't do that in my head, so let me break open a calculator to do it. So let's see, 16,400,000. Yep, it got pretty close. It didn't quite get the final steps or the quotient, but it got pretty dang close and showed you all the work that it did along the way. So that's kind of the reasoning part of a reasoning model is let's think through a problem in multiple steps before we spit out the correct answer. So how did DeepSeek-R1 get here? There's two main contributions of the paper. And the first one is kind of this big post-training workflow, large-scale RL that they did on top of their base models. And the second is the distillation of all these small models like the one that I was just running locally on my computer. And they state in the paper that the goal is to explore the potential of LLMs to develop reasoning capabilities without any supervised data, focusing on their self-evolution through pure RL. And, you know, Jan LeCun was kind of onto something back in 2016 when he made this analogy of the cake. There's the large-scale pre-training that we do on these models that is kind of like the interior to the cake with tons, millions, billions of pre-training tokens. Then there's the supervised machine learning on top that's, maybe millions of samples or a couple 100,000 samples. And then there's this reinforcement learning that's the cherry on top of the cake that really makes it a nice user interface and makes it easy to work with. So same process that Jan was talking about in 2016 is really what they're doing in this paper as well. And so when you look at the suite of models, there's a good few that were released. And so I started by just helping you navigate all of these. First, there's DeepSeek-v3, and there's a base model and a supervised fine-tuned model. These were actually released like the day after Christmas, Boxing Day last year, and didn't get as much hype as R1, but are super solid base models. And then there's R1-Zero, which is an RL model from this paper. And then there's DeepSeek-R1, which is an improved version of R1-Zero. All of these models are 671 billion parameter mixture of experts models with 37 billion active parameters per token. And they have a context length of 128K. Note, all of these models take like 670 gigabytes of storage if you're going to download them to your local machine, and you need like a cluster of GPUs to run them. So they also released this suite of smaller distilled models, which we'll talk about how we got them. But there's a 1.5B, a 7B, an 8B, all the way up to 70B. And what these models are, if you look at the end of the name, that's like the model that they started with. So they took Llama 8B, generated a bunch of training data from the big DeepSeek models, and then distilled these models, trained them further, and got some reasoning capabilities from the distillation. So I think it's good to even start with V3 base and V3 as setting some context. Basically, these models are just your standard transformer architecture. Not standard, they're a mixture of experts, which we'll get into in a second, but it's basically going through each token, each word, putting it into an embedding space, running attention on it, has a feed-forward layer, and then they're trying to update and predict the next word. So I like to use the example of Paris traveled to Paris, France, like Paris Hilton, and the meaning of Paris in the first word is different than the meaning of Paris in the second word. And transformers kind of look at the whole context and help you disambiguate each term as you're going along. Mixture of experts expands this or extends this transformer block to add, instead of this big feed forward layer after the attention heads, they split those into a bunch of different experts and have a router that can route each token to an individual expert. So when they say there's 670 billion parameters, that's like the whole model. And then there's 37 billion active parameters, which might be just these experts that are active while we're looking at each word. And then there's a router that says like, hey, which expert knows more about like entertainment versus geography? In theory, the router can route to the right experts who can help generate Paris, France instead of Paris Hilton. So that's kind of the intuition behind mixture of experts. And that's what those different numbers mean of 670 and 37 billion. The mixture of experts really help with both inference and training time. And so from their DeepSeek-v3 GitHub, they said DeepSeek-v3 requires only 2.7 million H800 GPU hours, which is the $5 million that you've probably heard floating around. But they said that the training process was remarkably stable with these mixture of experts. So that's one of the advantages of MOEs, is they're remarkably stable, cheaper to train. And they said throughout the entire training process, we did not experience any irrecoverable loss spikes or perform any rollbacks. So you can imagine with some of these other models that are harder to train, the cost goes up because you might mess up a training run or whatever. They said that this was just super stable. And a couple of the other optimizations that they did were they actually trained it in mixed floating point precision. So they used FP8 during the training framework. And they wrote some very low level optimization of the communication from the different GPUs in the clusters, because you can imagine you're going to have to serve all of these parameters on different GPUs, and being able to load different experts and different model weights and pass the data back and forth requires a lot of low level optimization of even just like GPU to GPU. So that's kind of how they got all of these performance gains. And I did a little math on what you would need to run the full shebang, like just for inference, not for training. So you could like run the whole thing on a lower, like without GPUs, it would just be extremely slow. But if you wanted a cluster of GPUs, an H100 has like 80 gigabytes of VRAM. So with 8 by H100s, you could almost run the full thing at full precision. And a cluster like that would cost $25 an hour, at least when I looked at it last. So that kind of gives you a sense of, if you did want to serve this whole thing, what you would have to do. So that's just for the V1 model. They introduced DeepSeek-R1-Zero in this paper, which kind of pays homage to AlphaZero. And the idea is that it required no bootstrapping and learned everything on its own, and that these reasoning capabilities kind of emerged without any labeled supervision of telling it how to reason through problems, which is pretty cool. And so how they did this was actually kind of mentioned in one of the previous papers that they released, and it was this DeepSeek math paper, if you're interested. But they introduced this reinforcement learning policy optimization called GRPO. And if you're familiar with reinforcement learning policy optimizations, you might hear like DPO or PPO. This is their version of it called GRPO. And this is what they use to go from DeepSeek-v3 to this DeepSeek-R1-Zero. And they have the equation for GRPO in the paper. It's one of those ones that like looks pretty intimidating when you first pull it up. But each one of the subcomponents are pretty easy to understand. So let's kind of break down what these are, just if you're looking at any of these equations in the future. Often you'll see this pi and theta, and that's like the LLM itself. That's the model weights. And typically you have like an old version of the LLM, like before you're doing the RL, and then you have the new one that you're training right now. And they have a nicer diagram in the GRPO paper that will help bring a lot of these variables to life. So in this case, they're comparing it to PPO, and they kind of simplify PPO by dropping out this value model. But basically, the pi theta is the model that you're training, and then pi theta old is the model that you're starting from. And then they take this A variable, which is what they call the advantage. And the advantage is like the reward signal that you're going to be feeding back into the model. And so pi theta is the policy model, pi theta reference is the reference model, and then you have this reward model. And in the case of R1-Zero, the reward model isn't even actually like a language model. You could have it be a language model, but in R1-Zero, it's just a bunch of rules that it wants the model to deterministically follow, which was super interesting to me. So in this case, they have kind of two things, two deterministic rewards that they're working on. It's what is the accuracy of the response? And this is only really applicable to math and coding. So like math and coding, you have the ability to either run unit tests on code, or in the case of math, you have like a final answer that should come out. And so for this R1-Zero experiment, they're just basically string matching on those things or running unit tests to determine that reward signal. And the other one is, did we put think open at the start, and do we have a think close at the end? Is there stuff in there? I actually found an example code base, which unfortunately isn't loading here. Maybe I'll just go to my Twitter real quick to show you guys.
And Greg, after this, we have a quick question too.
Yeah. Here we go. So I found this example code base for GRPO, and you can see there's like a correctness reward and a strict format reward. And basically these are just like regexes that give a numeric value for whether or not the thing got it right or wrong. So I'll pause there. What's the first question, Scott?
Sure. So Alex asked, do you have any intuition for why they can jettison the value function and still get good training? Have they done any ablation tests to compare to standard actor-critic models?
Yeah, so my intuition here is this only really works for math and coding, and math and coding require that you do a lot of reasoning. They actually state in the paper a little farther down that DeepSeek-R1-Zero encounters challenges such as poor readability and language missing. And so to address these, they introduced DeepSeek-R1, which is kind of fixing a lot of these issues. But they do say that like it's kind of removing a lot of, I forget what the actual wording they used was, but it's harder to optimize PPO than it is to optimize this GRPO because you have the additional non-determinism of the value model and the critic model for those other ones. That's at least my intuition there. So going back to these diagrams and going back to the equation, you have a query come in and you have your base, or you have the LLM that you're training generate a bunch of different outputs. You then run those outputs through either those regexes that we showed before or code interpreter or whatever, or in the case of some other reinforcement learning algorithms, the reward model might be an LLM. You also run it through the reference model. You make sure the new model that you're training and the reference model, they have this term at the end that is the KL divergence of those model weights so that the new model doesn't drift too far from the old model. And then once you have these scores that come out the other side from the KL divergence and the reward model and all of this stuff, for GRPO, they just kind of take this average. So for all of the rewards that came out of that big group of answers that came from that query, they look at the mean, they look at the standard deviation, and they look at the individual reward, and then that comes up with this A parameter that you have in here. And so this full optimization here is trying to minimize this kind of crazy function that they have right here. But hopefully that makes sense of what each one of those terms are in there. And I thought this was kind of the most shocking part of this section, was that the reward model wasn't actually a model being trained. They also do have, so you do have these signals right here, and I think it's good to mention that you also have the signal of the prompt itself. So in this case, they have a prompt that's like, this is a conversation between a user and an agent. User asks a question, agent solves it, and they explicitly state the agent first thinks about the reasoning process in the mind and then provides the user with an answer. And they give a little formatting there too. So you do have, you have this signal that's going into the model in the RL, and then you have this signal that's going into the like pre-trained model and just the next word prediction to give you a little more control. So putting that all together, they kind of had this aha moment that they show in the paper. You might have seen this in some Twitter threads or stuff like that. And it's kind of like they're comparing it to the move 37 moment in AlphaGo, except I don't think it was that crazy. But the idea is some of these reinforcement algorithms start to pick up behaviors or actions that weren't explicitly in the program or in the training data. So in AlphaGo, the system generated a move that had like 1 in 10,000 odds of being played by a human. But in retrospect, that move won the game for the model. And their version of this was, okay, we never explicitly had training data of the reasoning steps, because that's really hard to label. You'd have to have a human go down and like write down their whole thought process. They just kind of gave it questions and answers, told it to think about its steps, and then had this RL signal in between. And the aha moment that they had here was they were looking at some of these outputs, and they noticed that the model was like telling itself, wait, pause for a little bit, think about this. There's an aha moment that I can flag here. And then it reevaluated the steps that it had done before and changed how it was solving the problem, and then eventually got to the correct answer. I have seen this behavior in even that 14 billion parameter model that I was running with long division, where there was this one thread that I had it going on and it kept saying, oh, wait, that's not how I do it. Oh, wait, let me try again. Oh, wait. And then after that huge thought block, it finally got the right answer at the end. And this is kind of what people are talking about with this test time compute, is the model can now dynamically allocate how much compute it needs to solve a problem by looking at what it's done before, seeing if it needs to go revisit anything, backtrack, and do all these steps. So you hear about the aha moment, that's kind of what it was in this paper. So how does this translate to any benchmarks or any numbers? Well, they tried it on, or they tried R1-Zero on a few math and coding benchmarks, because that's kind of what it was best to do. And you can see that R1 slowly gets better and better at these AMI math questions, which is honestly this really small evaluation set. There's like 30 examples here, so the numbers would go up pretty quickly if you just get one more answer correct out of those 30. But at the end of the day, R1-Zero outperformed O1 Mini and was competitive with O1 on this benchmark, purely from bootstrapping with this RL process, which was pretty encouraging for no actual training data that explicitly said how to reason. Any questions there before we dive into the full R1?
Oh man, there's so many questions, but honestly, Eric is killing it in the chat too. I'll actually just use the last one. How does R1 perform on ARC-AGI benchmark, the one OpenAI demonstrated that they are on top of? Do you have any idea?
Yes, I know. I think the guys from Endia Labs actually put out a whole
Yeah.
tweet on that. What's the main guy's name? Mike Noob.
Yeah. KN. Yep.
Um, And so if you want to check it out, they have a R1-Zero and R1 results analysis. You can probably Google for this as well. And I technically haven't read this yet, so I'm kind of reading this real time with you. And it looks like R1-Zero gets 14%, R1 gets 15%. And so that's still a little behind O1, at least on this ARC-AGI challenge.
There was another question too about self-hosting DeepSeek for
Yeah.
inference. How much would it cost on AWS? Someone asked if it was $25 specifically per hour. And then maybe you also want to talk about other ways to interface with DeepSeek.
Yeah, so like I said above, that would be, so if you rented a cluster of 8 H100s, you could serve the model, and that's $25 an hour. So like rough back of the napkin math is you look at how much VRAM the GPU has, and then you look at how many parameters the model has. And so you kind of, if you want to run it at 8 F8, right? That's gonna be like a 1-to-1 mapping of the number of bytes you need to load into memory and the model size. So $25 an hour. And then what I was doing here is I was actually just using OLLAMA locally. So OLLAMA run, and I grabbed the 14 billion parameter model, and that's able to run on my MacBook or on this Ubuntu laptop that I have. So it's not the full one, but it is a distilled one, which we'll get into. Cool. So that's R1-Zero, not as well performing as the full R1 and mainly good at math and programming, which is still pretty cool. Like, I think it would be fun to do an experiment, especially with these smaller models that I can run locally on some lower resource languages. Like, we use Rust a lot at Oxen, and Rust has the Rust compiler, and we have like a bunch of unit tests for our code. There's a world in which we use that as the reward signal, and we use our own code to fine tune some of these things. And maybe that gives a better, chat completion model that you could hook into your VS code. So some of the things I was thinking about there of like some of those techniques could be cool to even make your own little chatbot, or sorry, code completion bot. But they say that R1-Zero style is not great at writing coherent text and suffered from this language mixing problem. So to fix this, they add in this multi-stage training pipeline and what they call cold start data. So the whole pipeline here looks like this. And so first they collect some supervised fine-tuning data, a couple thousand examples, and they train the model on that. Then they do the same kind of reasoning optimization that they did in R1-Zero, just to kick off the loop. Then they take that model and they generate another synthetic data set of supervised fine-tuning data with rejection sampling, and that gets 800,000 examples that then they supervise fine-tune the model again. They then go back to reinforcement learning, but in this case, they're doing it more for alignment to make sure the model is both helpful and harmless, and less of the reward signal that is like math and programming. And those are kind of the 4 steps that they took to get to the DeepSeek-R1. So let's kind of dive into each one of those buckets. So the cold start data, they said that they used a few approaches. One was just few-shot prompting with long chain of thought as the examples. So they took DeepSeek-v3, put in a couple examples to the context window of long chain of thought, and then used few-shot prompting for it to just generate more and more data that looked like that. So that was one way that they got the cold start data. They also did the same thing, but prompted the models to generate detailed answers with reflection and verification. So again, they're just using v3 to bootstrap data for R1. And they also gathered a bunch of DeepSeek-R1-Zero outputs and filtered them by human annotators. So this cold start data, they didn't give like a full number in the paper, but they said it was a couple thousand examples. And it's very curated, and they're using some prompting techniques to generate this data. It's not like fully human generated, but it might be human annotated or human filtered to make sure that it's like a really good starting point for this model. They also added in what they called a language consistency reward. So although this RL step that happens after the SF is like very similar to the R1-Zero step, they also add in what they call language consistency to keep the model more on track, because that was one of the things that they said went wrong in the Zero, is like it would switch back and forth between different languages. So basically, they just have a reward signal that is the proportion of target language words to non-target language words in the chain of thought thinking. And what's funny is they said that making it more consistent in the output language actually degraded the model performance on some benchmarks, but it makes it way more readable by humans. So there's a world in which like thinking in both Chinese and English made it perform better, but they were like, we want the outputs to be readable in whatever language it is. So they took the hit on performance just to make it more readable, which I thought was pretty entertaining. So then once they have this RL reasoning model with the cold start data that it's been trained on and the process from R1-Zero, they then do rejection sampling and another iteration of supervised fine-tuning. This is actually very similar to the thinking LLMs or self-rewarding LLMs papers that we've covered in the past. And basically, for rejection sampling, they have a pipeline that kind of looks like this, where they have queries that are coming in. They run it through the trained model that they got here and get a bunch of different outputs. And then they use DeepSeek-v3 as a judge to say, is this a good response? Is this not a good response? And they put that into the 800,000 synthetic supervised fine-tuning data that they use for this iteration of the model. So that's like step 3 in this process, was generate more synthetic data and then filter it down. Instead of using compilers or raw string checks, they use DeepSeek-v3 as a judge to kind of filter down that data. And that data is like 600,000 examples of reasoning data and another 200,000 that are more like factual question answer pairs, or even just like conversation, like, hey, how are you? What's up? That kind of stuff. And then finally, after they have this supervised fine-tuned model on the 800,000 examples, they do one more RL step. And this is more like your traditional RL pipeline and traditional reward signals. And these reward signals are to make sure that the model is helpful and harmless. So this is something that you can kind of define in whatever the prompt is for the judge. Like, you're just saying, is this response helpful? Is it not harmless? And then they use all of that data to do a final reinforcement learning loop on the model to get the final DeepSeek-R1. So in theory, there's a lot of different knobs that you could tweak in this pipeline. The prompts that you use for the LLM as a judge, how you filter down the SFT data. And the paper didn't go into too much detail on the prompts they used or the raw data sets. They just kind of like laid out this framework of how somebody else could do it. So that's kind of the whole takeaway for the reinforcement learning and R1, but what I think is potentially more interesting is this distilling of small models. So for the suite of smaller models that we talked about at the top, they simply used DeepSeek-R1 to generate 800,000 examples to fine-tune other open source models with. So fine-tuning Qwen, fine-tuning Llama 8B, Llama 70B, etc. And no RL was done in this distillation process. It was just SFT. And what's pretty cool, you see the suite of models here. There's the 1.5B all the way up to Llama 70B. And on Amy and on these math and coding problems, you can see even the small models that they distilled on the data that was generated from R1, and this is just like a supervised fine-tuning, even the 1.5B beats GPT-4o on Amy 2024 and Math 500, not on this one. So that's pretty crazy to me that you can just like generate a bunch of data from this massive model, do a supervised fine-tuning on the smaller model, and boom, it has this reasoning capability, and boom, it gets way better at these benchmarks. And so the natural question that arises there is like, okay, they just did supervised fine-tuning. Can a model achieve comparable performance through large-scale RL without distillation? So they were like, okay, that's super interesting. Just SFT bumps up the model performance. What if we took QWQ32B and ran it through the large-scale reinforcement learning pipeline that we talked about above with that cold start data, RL, SFT, RL, and doing that, they go from the preview version of this model to the distilled version. It actually doesn't get much better with these smaller models. It kind of stays relatively at the same performance. But if you simply use all of those outputs and do the SFT, it bumps up the performance. So my takeaway is like this large-scale reinforcement learning pipeline works really well if you have a really large model, like these big mixture of experts. But if you're doing it for small models, you might as well just do the SFT step and generate a ton of data from the large models. And since DeepSeek-R1 is MIT licensed, you don't have any of these like restrictions on using the thoughts or using it for your training data, which is pretty great for us developers that don't have big all access to compute. So yeah, that's kind of my big takeaway. I hope that you kind of got a sense of, if you're a big research lab, how can you set up these loops on these big models to really take them from, you know, an R0 to an R1. And I imagine that OpenAI is doing a similar thing internally for O1 to O3. But what's great for us is when they release those, then we can use those to distill smaller models that can run at home. And we're working a lot on pipelines to enable this at Oxen.AI, and we're actually partnering with some compute providers that are going to be able to run DeepSeek-R1 at full precision on a cluster of H100s. So if you want to be a part of any of those experiments or try any of the synthetic data that we're going to be generating from that, feel free just to like reach out to us at hello@Oxen.AI. We're like happy to give some free synthetic data and compute for feedback. So feel free to just reach out there. So that's all I have for the paper. I'll pause the recording, and I love to just do some asynchronous chat with the group afterwards. Hope you enjoyed if you're watching on the YouTubes, and we'll see you next time.